All right, so in this video, we're going to tie up some loose ends here on some polar graphs. The first thing I'm going to mention very, very briefly is the symmetry for polar graphs. I generally don't put a lot of time towards this because I find that putting the graph together is far easier than having to memorize a bunch of other stuff. You can certainly take a look at it on page 672. It is very intuitive. I said memorize a few minutes ago, but I really think if you take a little bit of time and look at it, you're gonna understand it pretty easily. So I would encourage you to take a look at that. There's a box at the top of page 672 that I think you should probably look at. Now, moving into something that is very, very important, and that would be polar slope. So we're going to talk about slopes of tangent lines, if you will, to polar graphs. And so I'll go ahead and I'll consider now the polar curve r equals f of theta. So if we remember, x equals r cosine theta and y equals r sine theta for polar coordinates. Therefore, what I have is x equaling f of theta cosine theta and y equaling f of theta sine of theta. So all I did is I replaced these r's with f of theta. Now the reason why that's important is because now you can see we have parametric equations, x and y with parameter theta. So if my job now is to come up with dy dx, that can be found by dy d theta over dx d theta, as we did in earlier videos. Now, to come up with these, it's going to be a product rule. So I'm going to start here, the derivative of y with respect to theta. So I'm going to have derivative of the first times the second plus derivative of the second back times the first. So derivative of the first times the second plus derivative of the second would be cosine back times the first. So there's our numerator now. And then for the dx d theta, derivative of this with respect to theta. So I'm going to have my derivative of the first times the second plus derivative of the second, which is a negative sine theta, back times the first. So here is your polar slope formula that you'll use in a variety of different circumstances. All right, so we'll take a look at a real quick example here. And what I have set up so far is just your polar equation. And we know that that's going to be our f of theta, our function with respect to theta in this case. And this is the formula that we just came up with. So it's really just a matter of, again, following the formula. Feels like the last couple videos before we got to the polar stuff was much of the same. You have a formula, you just kind of fill it in along the way. I'll do my best to show you where these formulas come from, but at the end of the day, it is just a matter of plugging stuff in, it seems like. So we've got our dy dx, and our f prime would be a negative cosine theta. That would be the derivative of this guy, followed by sine of theta. So that sine and that sine are the same. Then we'll have our plus f of theta, which would be 1 minus sine theta, times cosine, all over. Now we have a negative cosine theta again, but followed by another cosine theta. So derivative followed by cosine, derivative there, and there's our cosine. And then minus the function, 1 minus sine theta, and then multiplied by a sine theta. So again, really not anything crazy. Depending on the context that you're using this, you can obviously clean it up if you want to. Otherwise, this would be a reasonable unsimplified derivative for our polar curve.